Hi, good afternoon. It's Mark Ostrowski from Checkpoint Software. Today, we're going to spend 20 to 30 minutes talking a little bit about how cloud has changed cybersecurity forever. Again, Mark Ostrowski from Checkpoint Cybersecurity Evangelist, and I report out of the office of the CTO. So let's get started. So, opening up here, let's talk a little bit about the evolution of machine learning. A relatively high level picture here, but we talk about machine learning, big data, deep learning, and on these stages of AI over the past decade or so, a couple decades. And one of the biggest things that changed the course of machine learning, and we can give some credit to Google for this, is that being able to manipulate large amounts of data with the proper amount of compute was one of the biggest hurdles that certainly propelled us into the current age of machine learning and artificial intelligence. And essentially by taking data and breaking up into smaller parts and then applying strong compute enabled machine learning certainly to progress. And the era that we're in today is about taking the math, taking the large amounts of data and the ample amount of compute, and then using that from a context perspective to do some of the things we want to do and make the manipulations. So before we even get into cybersecurity, let's just take a very simple example around machine learning and the setup of it. So this example is specifically around images. So let's talk a little bit about the training phase. So in the training phase, you want to establish ground truth. You want to, in this case, take images, assign specific labels to those images. You want to put them through a feature extractor, understand the features, and then that becomes your machine learning and algorithm. So it's based upon data. It's based upon labels that are associated to the data, in this case, images, to be able to establish that ground truth. Once that function has been created, you want to move to the prediction phase. So the prediction phase should be where you have an image that you are not assigning ground truth to. You do not assign labels to it. And you want the function that you just created actually use the feature extractor and the features to then train and apply the specific labels. So a very high level example of machine learning, and you'll see how this applies to building your cybersecurity machine learning project. And again, another just sort of way of looking at this classic machine learning in two different types of supervised and unsupervised. So on the left-hand side, again, is that supervised method of machine learning where, again, you have ground truth, you have labels, and then from that result, you can have classification and perhaps regression. Where on the right-hand side here, you can see a machine learning type that's unsupervised, again, giving it unclassified, unlabeled data, and then you can see what can happen relative specifically to cybersecurity, where you can use the data that's been learned from the algorithm and the function to then do things like anomaly detection and look for things that are clustered from a context perspective again, to assign those specific labels and identify perhaps a cyber threat. Last slide here before we actually get into the cybersecurity aspects in the machine learning project are just some tasks relative to cybersecurity and machine learning. So I'm not going to read through this slide word for word, but some of the key things on the left-hand side here: prediction, prevention, detection, response. The couple of examples we'll talk about today are around prevention and detection. And then actually we'll talk a little bit around the prediction aspects of it as well. And you can see here, the second dimension from a technical perspective, we can talk about WAF and firewalls and network traffic analysis, which is actually the exact example that we'll discuss next here. And then finally, the third dimension is how can we use these machine learning algorithms for cybersecurity attacks, specifically to things in transit, at rest, or historical, for either dynamic or static or reputation-based alerting. So let's dive into machine learning specifically in cybersecurity. So this is actually a machine learn project here we had at Checkpoint. Those of you familiar with Checkpoint, you'll remember the name Maggie, which was the name that we picked this specific machine learning project. We actually started this back in 2018, so we're a couple years in the making of this specific project, and we actually this project turned into general availability product. But specifically, I want to talk about how do we start this project. So we picked a name. We grabbed the correct mathematic resources, whether they're human resources, obviously, to be able to do the work, as well as the basis of the algorithm and the math. We use the experts for the topic, and the key here is they have lots of data. So let's talk to the next step of building your machine learning project. So we talked actually just a couple slides ago about supervised and unsupervised. So we started a supervised machine learning model with lots of data, like I mentioned. And again, in the cyber field, these samples and this data is very expensive. And from expensive, I mean in relation to the time it takes to investigate, the amount of information in the context and the deep learning associated into the samples, and of course money. You have to establish. Obviously there are things that you can grab that are just part of either your own research or through public areas where information and IOCs are shared. But also you want to be able to get specific samples that maybe you are pulling in from third parties. So they're expensive both from a money perspective as well as from a time and human capital perspective. And often the label is not accurate. So the concept of building the supervised machine learning model is something that, again, is very expensive. So what did Checkpoint do as is in this example, and what was the approach? We built this initial model with the samples labeled by a set of logic. So I mentioned early on the ground truth. We reported the infections to the customer, right? So again, this is a cybersecurity machine learning and algorithm looking for compromised hosts that may have been in a network for months, weeks, maybe even years, or it could be even days. So we reported the infections to the customer base and let them fill in the true label of the sample, meaning if that particular host, based upon the data we're looking at and the information that we're receiving from a malicious or threat indication perspective, they were able to affect the true label. And then we would then insert those samples back with the feedback into the data or into the algorithm to train and to make a better model. So this is the curse of cybersecurity machine learning and how expensive and how complicated it can be to create a specific model that gives very accurate results. So for 3 months in 2018, when we started this, and of course it matured very much into the end of 2019 and all of last year and into the beginning of this year, just to give you an idea of scope for the specific project, we involved 33 customers. 1.5 million logs were analyzed. You can see here that there were some endpoint logs associated to that, not just network security logs. Again, this is ubiquitous across really any platform, whether it's cloud or on-prem or endpoint or mobile. And out of the 1.5 million logs, 740 of them were found to be infected by Maggie. So the false positive rate, if you do the math, was just over 1%, which in normal terms, you would think that's a pretty good false positive rate. But the goal was to provide very, very high levels of precise reporting of infected hosts. And we want to improve off of that 1.12%. And again, this is where we have the ability to take the data, take the samples, resubmit them with context to be able to drop the false positive rate. So before we get in, into a little bit of what this project resulted into and how it's tied to cybersecurity and specifically the cloud, this chart here very simply depicts on the right-hand side, basically two values were returned as part of deterministically to part of the algorithm, whether they're infected or not infected. So they're really 0 or 1. So on the right-hand side, you see 1 are all the returns that were indeed found malicious. And then on the left-hand side, starting with 0, are all the returns that were determined not malicious. And what you see here in the middle, obviously between the 0.5 and the 1, just that general area, are all the areas in which by tuning the algorithm, adding context, adding precise data to the ground truth data, you see that what you want to be able to attack is that middle ground. And once you attack that middle ground, you'll then create a highly efficient and precise machine learning an algorithm which will give you the false positive rate that you're looking for, right? So for us, our goal was to be less than 1% or in fact a 10%, where then you have on the right-hand side all malicious proven samples, and then on the left-hand side, you have samples that are non-malicious. So the result of our machine learning project was a cloud service. Again, the title of the presentation of how cloud has changed security forever, that this particular service that we released was 100% cloud-based. It was done in a fashion where the information that could be proprietary or of importance to the customer was 100% anonymized. But we're able to provide a service in which the customer can find the old saying, a needle in a haystack, where an average network of a couple thousand users creating 10 million logs a day, an algorithm was able to identify just the truly infected host using the algorithm. And you can see here that this animation, if it comes through, that you can see just the specific hosts that were infected versus the ones that were not, and then what that relationship was to all of the hosts that were trying to participate in the spread. So again, from millions of logs to only real threats, some more statistics: 59 million logs across an average week across endpoint, cloud, mobile, and IoT. You have the amount of activities, the targeted assets, and then the infected assets. So if you think about this from a couple of different angles relative to cybersecurity, is you want to separate that noise to the actual infected assets, not an asset that actually goes to a malicious site and never becomes infected, but the actual infected assets. And also just from a pure cost perspective, you want to eliminate or reduce the amount of logs that you're perhaps sending to a third-party application. So therefore your consumption model relative to cost becomes less as well. So truly models like this in machine learning will affect how we look for infected hosts and how we use infected host information. Leveraging cloud services like really will change how we triage events moving forward. So again, last slide before we change topics a little bit and wrap up with another example relative to big data, which is very much part of this an algorithm and machine learning project we just spoke about. We want to expose the stealthiest attacks with high precision. So you can see here that we were able to, with our machine learning project, be able to reduce the 1% false positive rate to less than 1%, in fact, 1/10 of a percent, by again leveraging the supervised and unsupervised machine learning models to enrich our ground truth with a better context, and over time building a better model, a better function, and then go forward get a better rate of detection. This cannot be done without big data analysis, and we'll talk about what those numbers look like purely from a checkpoint perspective as an example. We can do this, and we mentioned this on that one slide talking about cybersecurity risks relative to machine learning world, right? Real-time internet traffic visibility. We're covering enterprise-wide, and we want to have this be 100% be AI-based incident analysis. So this has been done without, again, having to require a supervised model, where we're at the point now where we're able to consume unsupervised and non-labeled data and be able to give very specific malicious or AI-generated verdict. So with that, let's change topics slightly, and again we'll wrap this up. We'll talk a little bit about the big data aspect in cloud security and what that translates to. So from a checkpoint perspective, Threat Cloud is where our threat intelligence cloud and where all threat intelligence lives. And you can see here it's comprised of things that we talked about on onset of this presentation. We have external feeds, we have AI enrichment like I just spoke about, we have predictive intelligence, and we have hundreds of millions of devices, whether they're clouds or gateways or endpoints or cameras or IoT devices, that are generating a huge amount of data. And down here in the bottom, you see from a daily perspective, trillions of logs, right? Tens of trillions of logs, billions of IOCs, almost 100 billion IOCs, a couple billion attacks, and 3 billion infected websites and files. So you can only imagine that if you relate this to the machine learning concept we spoke about in building a better machine learning and algorithm for AI-driven detection, you need lots of data. And certainly here, this is a lot of data, right? This is the big data aspect of that previous slide. So we can apply this big data to our machine learning projects and our AI-based detection. And it's a way of having those large amounts of data, good math, and large amounts of compute that exist obviously in cloud environments today, to be able to use it to do what I just spoke about. But also we can use big data specifically through talk about employing security inside of the cloud, right? So the examples that I'll give here, let's talk into the context of public cloud security, where you want to apply a level of network security and gain visibility to your Azure or GCP, or AWS environments. You have items of compliance that you want to be able to apply from a cloud security perspective, and then obviously having privileged identity protection. Think of IAM role safety, are just some concepts inside cloud security that certainly are pretty common in the marketplace today. But the piece that I want to speak specifically towards here is the cloud threat intelligence, right? Being context-aware security intelligence, and how we can use, again, big data and the information that I just previously spoke about relative to Threat Cloud, using that big data, using context-aware security intelligence to provide a very, very accurate cloud threat intelligence, again, in real time, and be able to provide prevention as well as predictive analysis. So let's look at a couple examples here as we put cloud security into context. In this case, we're talking about public cloud security. And you'll see here on this screenshot that we're able to break down the context into actual security insights. So I have two examples here, and then I'll wrap it up and talk about, again, the two use cases. So the first use case here, as you see here, what this depicts is somewhat of a network security analysis, right, or depiction where you have an external malicious host, you have an internal specific IP in this cloud-based environment. This is obviously an AWS-based environment based upon a Lambda functions you see here on the right. And what this use case shows is that you can use the big data analysis as well as the context-aware analysis to see outbound traffic to malicious IP addresses. So on the right-hand side here of this particular depiction, right, or screenshot, you have functions, you have instances, and those instances are talking out to external sources to a malicious IP address. So this just shows how you can use cloud visibility and posture management to identify and gain visibility into the specific assets in the cloud. But you can also associate that traffic outbound to malicious IP addresses that are then being identified as malicious, of course, through context-aware algorithms that we previously spoke about, to a large amount of big data threat intelligence cloud. I know I threw a lot out there, but that's what you're seeing here. The picture seems to makes it look a lot more simple, but behind the scenes, there's a lot going on. And just one thing, one piece of that context you see here is relative to, what country, for example, are involved in these both AWS assets and the malicious asset itself from the outside. The second use case is actually a very, very important use case, right? Is accepted inbound traffic from malicious IPs. So this is perhaps even more important, even though obviously outbound to malicious IPs is certainly relevant as well. But this is where malicious IP addresses actually have inbound connections to cloud assets that, again, exist in this particular case inside of AWS. And you can see the top accepted use ports on the right-hand side and the amount of accepted and rejected. If these were all rejected, it wouldn't be a big deal, but of course, in this case, they're accepted. So this again shows how you can take big data analysis, you can take machine learning, you can take context-aware threat analysis, and in real time give predictive and preventative measures to block this malicious traffic into these cloud-based assets. Just another example of how really the cloud has changed security forever, which is the second to last slide here. So again, I want to thank you for the time today, talking a little bit about machine learning projects and talking a little bit of how we can apply machine learning projects to cybersecurity, as well as looking at big data analysis of threat intelligence, and how if you tie that all together, you can have some really good visibility as well as preventive capabilities in cloud security, as well as on-prem devices or remote devices or devices that are outside of the edge that potentially are infected and malicious with malware. So thanks again, Mark Ostrowski at Checkpoint, and have a great rest of the day.